Welcome. In this video, we will look at some of the practical applications of deep learning and build a professional solution on computer vision. Before we get started, just a quick overview and the background of the website AI for Everyone, meant to be used for purely educational and non-commercial intent. This video is dedicated to the visual impaired community. The purpose of this website is to use AI for good causes and solve some of the problems that is facing humanity. And in that order, we want to democratize the talent to as much as needed so that everyone could be empowered to create an AI solution in the space that they feel is needed. And towards that, we'll be building some very futuristic prototypes using AI, deep learning. So why do we want to democratize the AI talent? Why are we sharing this completely free online? It's purely because the more the talent in AI, the better the solutions. There are a lot of major problems facing humanity. Sustainable development goals needs to be achieved. The AI for Good Global Summit has captured some of these problem statements, and we believe we could create solutions towards the global good. And some of the videos created in this series would help us move forward in this direction. Anyone watching this would be able to develop solutions in AI for Good theme. The SDG, Sustainable Development Goals, is put together by the UN, the UNICEF organizations to transform our world to be a better place. The vision cuts across 17 themes starting from hunger, health, education, gender equality, and environment. This video we will look at an app idea, a smartphone app that can check your health as you take the selfies. Diabetic retinopathy has been one of the most important causes of blindness in working people between 20 years and 74 years. And the numbers by 2030 would be 11 million. We are in a game to fight this battle. Google has already implemented an interesting deep learning algorithm to identify and screen patients right where it's happening. Now we can take that even further to the next level. So next time you are taking a photo, a selfie with your friends, this particular app idea is to detect diabetic retinopathy as you take your selfie automatically. So every time you take a selfie, you are screened for potential threat to your eyes and thereby able to detect diabetic retinopathy quite early and prevent blindness. The idea here is to take the neural net model that has been developed by the Google DeepMind research work in diabetic retinopathy and take it further so that it is available at the time of clicking photos in your smartphone, thereby screening at your home to check if your eye is healthy or you need to go for an eye checkup. The earlier we detect, the better the state of the health for the humanity. So we will look at some very interesting techniques where we'll do transfer learning from the work that Google retinopathy team has done and then move it to the next level for screening at your smartphone. So the deep neural net would be able to now predict if you need to go for a checkup of your eyes as you take some of the photographs in your casual settings. The project is about fighting blindness with deep learning application that you can build on your cloud and then use your smartphone to actually connect to that. There are interesting projects that's happening around the globe on the smartphone hardware that allows you to pick up retinopathy images from your smartphone. So here is how we can together work on this deep learning solution to build an app on your smartphone to fight blindness for humanity. The app is very simple. It takes 2 clicks. The first click, it picks up the photo as usual in the selfie. The second one, the camera would zoom down into the eye and if possible on the retina and pick up additional visuals from there. Since the architecture consists of 2 sequential networks and then a layer to merge these 2 classifiers to produce the final output. The idea is very simple. In the first network, we would actually do a face ID to identify who is the person, and based on that we'll be able to pick up whether he's a diabetic person, and if so, look for diabetic retinopathy screening, otherwise probably screen for cataract and other eye diseases. And in the second network, we actually would take up the diabetic retinopathy screening and check if the patient or the user here needs to be referred to a doctor or not. And the ensemble of these 2 classifiers would be the output that you would see on the UI in this smartphone app. So here in the diabetic retinopathy neural net work that has been already done by Google DeepMind, we would just take that and possibly repurpose it so that it is available for use at your home. So in this video, you will be able to jumpstart on your solution developments towards such practical problems. We will look at how deep learning could be used to do computer vision, essentially image classification, and build out how do we actually build a practical solution using existing work that has been already developed by various other industry and researchers, and then actually be able to get into a hands-on code lab where you can actually start experimenting it right away. The whole solution will be built on Keras and will have TensorFlow as the backend. So this whole video is about image classification for small data sets, which is essentially the kind of problems that most of us would face in a professional context, where we'll have limited amount of photos or data sets that's available for us, and we'll be able to do an image classification even though we have a limited amount of data. That's because the deep learning neural nets are repurposable. You would have often heard that we need a lot of data for deep learning to be successful. Most of the times we'll be constrained by availability of little data. The number of photos that is available for a particular image classification problem might be limited, and that would be a common scenario for most of the use cases that you might come across in the practical life. Never worry. Deep learning models are repurposable. Essentially, that means you can take a network that is trained on millions of images and then use that or repurpose that with your particular context, although you might have only thousands of photos or even hundreds of photos. So this whole concept is very crucial for you to succeed in the deep learning space, where you would take a pre-trained model which is available from a large data set and be able to leverage that or transfer the knowledge that is there, or transfer the representation from that original classifier into a new classifier or a new model that you are building, There is a lot of effort that has already gone in diabetic retinopathy, creating the data sets as well as developing the neural nets. For example, Google has worked with Arvind Eye to actually enable health screening camps in rural areas of India. And out comes 5 different classes in this particular model. Now we want to take this particular neural net and then repurpose it so that it can be used for your smartphone and only take recommendation whether your eyes are healthy or you want to go for a checkup. And so that's what is we'll be doing right here. We take the amazing work that has already gone in and just repurpose it so that we'll be able to see whether you need a checkup or not. The current classifier here would give us 5 classes in terms of the severity of the disease. We would want to remove that particular layer and then repurpose it so that we just check whether you want to go for a checkup or not. And this needs to be happening on your home use model or personal use model rather than a health camp model. So the enormous work that has already gone in is repurposable into other use cases. That's the point we want to take home here, where we'll take this existing neural net, freeze all the layers, and then just use the last layer, which is essentially a set of dense layers, to change it to this particular scenario of home use. Also, we need to wisely choose the objective function so that you minimize the false negatives. And so simply, the earlier network had a multi-class classification of 5 different classes, and now we are changing it to a binary classifier of 2 classes that just recommends whether you need a checkup or not. One of the key things is to choose the right objective function in the last layer. So this is a ready-made cheat sheet that you can use and refer back anytime you want to pick up which loss function to use in what kind of problems. The solution consists of merging 2 sequential networks. The first one to look at the face, and based on the face you know who is the person, and based on existing records you know whether he's or she's diabetic, and based on that you can either screen for diabetic retinopathy or for cataract or other eye diseases. The second sequential network looks at the eye in particular and then wants to check whether you need to be referred to a doctor or not. So the Keras provides a simple approach to actually merge different sequential networks using few lines of code. If you're looking at to develop a professional solution that is of state of the art, you can use this toolbox. The toolbox is a bag of 3 tricks. The first one is feature extraction, the second one is fine-tuning, and the third is data augmentation. Feature extraction is essentially using an existing pre-trained classifier which has been trained on a large data set like 1 million records, and use that or repurpose that for this particular new context. 2 approaches. The first one is just to do the feature extraction, which will get you a very good accuracy, but if you want to do the state of the art, you want to do the second approach where you do both feature extraction as well as fine-tuning. In this approach, we will be taking the existing pre-trained model and freezing the first few layers but retraining the last few layers. In a convolution network, the first few layers represent generic abstractions such as edges, textures, things like that, while the last few layers represent more hierarchical features such as ears, eyes, faces, those kind of things. Now, in your particular use case, if the original pre-trained model has been trained on a completely different set of images in comparison to what you already have, it is always recommended that you actually retrain the last few layers so that you are now able to repurpose the convolutional network for the particular set of visuals that is in this particular situation. Problem statements like this, where we are just changing a classifier from multi-class to binary, we would just want to retain the existing convolutional base as it is and just change the last few layers of the stacked dense layer. So this is pure feature extraction and just changing the last classifier. So we could just do that by doing include top equal to false in Keras. That will remove this last layer of dense stack, and then we'll be able to add our stack of dense layers as per the number of classes that we want to use. Here we just want to use a dense layer with one node because we just want to classify binary. Most of the times you want to repurpose the neural network by even retraining the last few layers of the convolutional network. This produces better accuracy and customizes the model for the set of visuals that you already have in your particular context. And this is a recommended approach. So this approach, we are doing feature extraction but also fine-tuning so that we are replacing the last few layers of the network and retraining that. So this approach is recommended generally, and we do that by just swapping the last few layers to be trainable. And the first few layers are frozen while the last few layers are trainable. The final approach in our toolbox is data augmentation, where we would just use different variations of the existing image, maybe flipping, rotating, and being able to use that allows us to provide a lot more input data sets. Surprised by the accuracy of the result on how well a computer can predict even beyond human level eyes. You need to know why the CNN works in this way. The visual world is fundamentally translation invariant. Also, the visual world is fundamentally spatially hierarchical, and CNN is able to do both. The visual world is fundamentally translation invariant. That means the visual can be viewed from different angles, and the CNNs would be able to detect that. Next, the visual world is fundamentally spatially hierarchical. That means the first few layers of the convolutional network can learn the edges and the texture and the colors, and the next few layers can, example, learn about the shape like circles and the shape of the lips, and the next few layers can learn even higher level abstractions such as eyes, ears, mouth, and even the final layers can learn about the face itself. So this is how a CNN is able to more accurately perform than a human. See how to do the feature extraction, where we are looking at how to change the last set of dense layers from a multi-class to a binary one. So the idea is quite simple. We take the existing convolutional base and just say that we don't want to include the top dense layers, and make sure the convolutional base is non-trainable. That means we just are going to reuse the existing convolutional base as it is, but then just add the set of dense layers, and here we need a binary classifier, and that's what we are going to set the last layer with single node and with a sigmoid activation function. And so we get a final network that is a convolutional base followed by a layer to flatten the input, and then a couple of dense layers with the final dense layer having a single node. So essentially this is what we did. We have the existing convolutional base but just have swapped out the top layer with a new one. Times we'll be repurposing the neural network by even swapping out the final few layers of the convolutional base. This is often used in scenarios where the image set in your particular use case is slightly or completely different from the original set of images that the original pre-trained model was trained on. And so quite simply, we take the existing convolutional network and then just make sure the last few layers are trainable. So if you look at the number of layers that is trainable and non-trainable, you see we have made sure the first few layers are non-trainable but just made sure the block 5 is trainable, and then we stack it up with a set of dense layers as usual. So in this particular scenario we are able to take the features of the first few layers of the convolution network, retrain the last few layers of the convolution network, and then finally stack it up with a set of dense layers. So this will produce the best state-of-art accuracy, and it's an essential approach that you would use, especially if your visual world looks very different than the visual world that the original pre-trained model was trained on. Now let's see how we can develop this complete working sample. We define the problem. Here is to develop a binary classifier based on ImageNet database, which uses all the 3 techniques that we learned in the toolbox. Prepare the data and then design the network. Let's see how the data looks like. And again, in the test data set, let's see how the pictures looks like. These are completely different set of visuals here. So the neural network needs to learn the general patterns or the general appearance of a cat and then being able to predict that. Here is a full code sample. This is an virtual machine on Azure, data science virtual machine. You could take this free from Azure for a limited time. We are now running on a NVIDIA GPU virtual machine. So we are going to use the VGG as a convolutional base. We're going to swap out the top layer with a set of stacked dense layer, and we're going to change the 5th block, the final block of the convolutional base, and train it. So if you look at it, we are setting the 5th block as trainable, and we just print it out. Let's see. So the 5th block has been set as trainable, whereas the previous blocks are all non-trainable. Then we add the set of dense layers, and here is a summary of the network. We have a VGG as a base, the convolutional base, and then a layer to flatten, and then a couple of dense layers with the final layer with single node for the binary output. The VGG network has the 5th block as a trainable block. So we have actually in fact used both feature extraction and fine-tuning in this architecture. The next step is to compile the network, and we are using data augmentation, the 3rd technique in the toolbox, to actually flip the image and rotate it a bit and then feed it into the training data set. Next, this is we just want to make sure how the generator looks. So this is the generator, and we are taking images of size 150 by 150. There are almost 2000 images belonging to these two classes in the training data set. Next, we run the training by just saying fit generator, and the training has started. This is running on a GPU server. It will take some time for it to go through the 100 epochs. The training runs for a few hours on the GPU net system, and here we are going to plot the accuracy and also then evaluate the network against the test data set, and then we want to make sure the test accuracy is good enough. Finally, we save the model, and the model is ready for prediction. We'll try out few samples and check if the prediction is right. If you look at the test accuracy, it's around 93%. Pretty neat. And this is how it has evolved over the epochs, the accuracy metrics. And in fact, it has predicted quite accurately. Immensely thankful to Francois for his amazing book, Deep Learning with Python, essentially the best book I've ever read on Keras, making it quite simple and effective to learn and understand. And most of the code samples we are looking at in this video series are directly from this book. We immensely recommend this book for anyone trying to do practical deep learning.